So most of the time when we're looking at probability and random variables, we're not given a distribution. We're not given this full, beautiful table because one, a lot of times we just don't know the probabilities. And two, sometimes there just might be so many outcomes that it doesn't make sense to write them all on a table like this. So there's so many different special kinds of random variables, okay? And here we're going to talk about geometric distributions, Bernoulli trials. We're not going to worry too much about the lingo here in this video, but just using it to introduce a very, very special one in the next video called binomial distributions. Again, there's that word, distributions, the description of the randomness, okay? Distribution means what are the values and how are their probabilities kind of distributed, spread out, okay? So this is really just an introduction to that really special kind in the next video. We're going to start by talking about something called Bernoulli trials. And again, it's not super important, but when we do that, these things have 2 or 3. I know you see 3 right here, but you'll see why I say 2 or 3 requirements for something to be a Bernoulli trial. So each trial, and again, when we say trial, we mean like attempt. Trial is a formal word, but it means attempt. So repeated attempts of an experiment are called Bernoulli attempts, if you will, if the following conditions are met. We only are interested in success or failure. And we can define those however we want. Success can be whatever we want. Maybe success means rolling a 5 on a die. Maybe success means rolling 52 out of 10 dice. I don't know. We can define success however we want. Maybe it's heads on a coin. But we define it so that there's only success or failure. And the probability of each of these successes is going to be the same for every trial. Okay, so the trials are independent, because if they weren't independent, then those probabilities might change. So 2 and 3 are really very, very similar, very, very closely attached. Let's see an example here. Let's say we're looking at a basketball player and she makes about 62% of her free throws. Normally this is not independent, but we're going to assume that these shots are independent. Find the probability that in tonight's game, she'll do the following. So it's a probability that the first free throw she makes is on the 4th attempt. So let's step away from random variables for a second and just think about this kind of intuitively. You make 62% of her free throws. What's the probability that her first free throw success is on the 4th attempt? Well, what has to happen for this to be the case? We're looking at the probability of something. Well, if her first success is on the 4th, that means she must have failed the first 3 times. So we can rewrite this as failure, 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 success. If her first success is on the 4th attempt, the first 3 must be fails. This is what we're looking at, the probability of this. Well, we know they're all independent, so that's just going to be multiplying each probability by itself, right? So another way of writing this, by the way, right? The probability of success is P, and the probability of failure is Q. Just like I think we've done this before, P and Q. Maybe not. Q is 1 minus P. Q is just not P. So if it's either success or failure, they have to add up to 100%. So here, P is 62%, 0.62. Q is the probability left over. 1 minus 62%, that's 38%. So what we have here is P times P times P. Sorry, those are Q's, probability of failure. Q times Q times Q is just Q cubed. That's kind of fun to say, Q cubed. Times the probability of a success, which is P. Well, that's 0.38 cubed times 0.62. And we could use our calculator to find this out. Oh, whatever. 0.38 cubed times 0.62. That's like a 3% chance, 0.0340. Right, about 3.4%. Pretty unlikely. Pretty unlikely that her first success is so late in the game. She's pretty good with her free throws. All right. And that's how we do it. Just to remind you why these are Bernoulli trials. Each trial, each attempt, each free throw only has two possible outcomes. It goes in the basket, it doesn't go in the basket. We're going to count going in as a success, going out as a fail. And the probability of each free throw, P, is the same for everyone because we're assuming that the shots are independent. And that also takes into account number 3. So these are Bernoulli trials. Technically, this is a geometric random variable, but we aren't going to really talk about that. Now we could do the same process for letter B. Okay, pause the video, try to do this on your own, and let's see if we get the same answer. Well, the first free throw on the 12th attempt, oh gosh. All right, well, that's going to be very similar. That means we need 11 fails. I'm not actually writing out 11 of these. Say this is 11 fails. So very similarly, it's going to be q to the 11th power times 1p. And you're going to see the pattern here, right? The probability of the first free throw on the 6th attempt would have 5 fails and then 1 success. So we just go through this again, change the first exponent to 11th. We'll get a very, very small number, 0.000015. It's so unlikely that she's going to miss so many before finally getting one. So this is really leading somewhere. Here's where it's leading. First, we looked at what's the probability that the first success happens on the 4th one. It doesn't matter what happens after that 4th one. First basket on the 4th try. Well, what if we wanted to know the probability that she made exactly 1 basket in 4 attempts? This isn't the same thing. Now it doesn't matter which one she makes, only that she made exactly 1 out of 4. So what are the possible combinations for that to happen? Well, we have the combination that we talked about earlier. Miss the first 3, get the last one. But the success could also come on the 3rd shot. The success could come on the 2nd shot. The success could come on the 1st shot. All that matters is that she makes 1 free throw out of 4 shots. And this combination is where we're going, okay? And it can get tedious. So this one's not too bad. There's just 4 ways that it could happen. So to find the probability of this, each of these has the same probability. We just add them all up. It's just 4 times the probability of one of these happening. But if we looked at like the probability of 5 successes out of 10 shots, that is a nightmare to calculate by hand. We have some mathematical shortcuts. We're going to skip even the mathematical shortcuts and just use computers. But this is really what we're going for. Okay. This right here is an example of a binomial random variable, a special random variable, a special discrete random variable with really cool rules that's very common and pops up in a lot of different places. We'll see a lot of examples of that. And it's the reason why it being special is nice because special random variables, special cases of probability have really cool shortcuts that let us save so much time and effort. And we'll see those in the next video. Stay tuned.